Go ahead.
All right. Well, I'm Dick Sauer, and I was at NASA from 1967 to 1999. One of my primary duties was the manager of the water system as far as the quality aspects are concerned. I worked in the medical directorate and the various names that we call the medical directorate through all those years. When I came, Mercury was completed, Gemini was completed, but we learned a lot of things during those flights that contributed to the design, eventually, of the shuttle system, which we'll be addressing. John's going to address that to some detail. The early mission, Mercury, was a very simple system from a water standpoint. There was a bag of water that the crew sat on, and the seatbelt tension forced the water up a tube that the astronauts had a little bite tube that they could drink from this sack of water. The quality of the water we really don't know, but it was probably okay. We had a pretty innocuous water container that didn't contribute to any contamination that we knew of to the water. Gemini program was much more advanced. We attempted to use fuel cell water at that time, but because of some problems with the membrane in the fuel cell, we always had an organic contamination. So all our water that we used on Gemini was stored water that was added to the system at launch. We did notice that during the Gemini program, we did have some microbial contamination that we recognized, and that forced the design in the Apollo to use in the Apollo command module and the lunar module to use disinfectants for the water. In the Apollo program, we were able to use the fuel cell water, which was very good quality, and we had the crewmen add chlorine to that water once every 1 day in an ampule form, and that had to be added because there was a potential cross connection between the potable water and the urine dump system. That system worked fairly well. It did involve a lot of crew time, which was a very high demand at that time, which it always is. So that led to some designs in the shuttle program in particular to try to eliminate as much as possible crew intervention to maintain water quality, so it'd be on a passive role. Also in Gemini, we recognized a potential of dissolved gases coming out of solution, and that really became an issue during the Apollo program. And the problem was that the membranes that forced the water out of the tanks, because we use air pressure over a water bladder, and those bladders would all be permeable to gases to some extent over a long period of time. So we were forcing gas into the water, as well as we were carrying some gas over from the fuel cells. And that led us to develop a water separation system that we used successfully in Shuttle that John will address. The lunar module used iodine as its disinfectant because we had to store water some 30 days ahead of time in the lunar module for drinking purposes, and the iodine was much less reactive than the chlorine. So that's when we adopted the iodine in the lunar module, which then, because of that success, we were able to use in Shuttle. And I might add in the workshop, on the space station workshop? Orbital workshop, Orbital workshop, OWS. The Orbital workshop, is that the right name for it?
Skylab.
Skylab, that's it. Skylab, how quickly you forget. That was the original name of it, was Orbital workshop. The Skylab, all the water was stored on board the Skylab at launch, and that supported the 28, 56, and 83-day missions. And we recognized the potential again for gassing the water through the membrane, so that's when we started using a metal bellows positive expulsion tank. And that worked very well. And we decided we were going to make the entire system out of stainless steel, and that almost eliminated all the iodine depletion, or at least it lowered it to a degree that we could maintain iodine during the hiatus between one mission and the other. We did add iodine periodically in the in the Skylab missions with a little ampule system, and then we had an iodine comparator on board that we could tell what the iodine levels were. Because the entire system was stainless steel, we had virtually no mineral contamination or element contamination. There was a potential, I think, for nickel contamination, but that it never really became an issue. And those lessons are what we used when we designed the shuttle system. We used the iodine as in an active role. We developed an iodinated resin through which the fuel cell water flowed and then stored on board for consumption. We eliminated as many cross-contamination points as we could. If we developed a cross-contamination need, we always isolated it through an iodinated filter, the microbial check valve we called it. And again, we made sure the entire system was stainless steel, and used again the metal bellows for positive expulsion tanks. And we had a good sampling system, sampled extensively pre-flight during the servicing procedures, and brought back periodic samples in flight so that we'd know what was going on, or brought back post-flight so we'd know what was going on. And that pretty much brings us up, I think, John, to your part of the stuff, your talk.
Okay. I'm John Schultz. I work for Wiley Integrated Science and Engineering. I've been here at the Johnson Space Center helping in the water quality area since 1987. And I've been working that same role all the way through until today, which is 2010. I want to just continue on and talk a little more about the shuttle system. Like Dick mentioned, the potable water for the shuttle is generated as a byproduct of electricity production by the 3 fuel cells. The fuel cells produce water at approximately 12 pounds per hour. The fuel cell water may contain some gases, and one of the particular concerns is hydrogen. So the fuel cell water passes through 2 hydrogen water separators to remove the entrained hydrogen gas before entering the 4 water storage tanks. There's 4 metal bellows storage tanks that we just call A, B, C, and D. Each tank has a capacity of 165 pounds of water. The supply water system not only just supplies the potable water, but it provides capability to provide overboard dumping of extra water. We supply water to the flash evaporator system for vehicle cooling. We supply water for the extra vehicle mobility unit recharge and for water transfer to the ISS, the International Space Station. And we also supply the chilled and ambient water to the Galley for crew consumptions and personal hygiene. The next slide shows a diagram of the system, showing the fuel cell water going through the hydrogen separator, where it is split into going to either tanks B, C, D, or into tank A. Tank A is the potable water tank. On its way into tank A, the water passes through what's called a microbial check valve, which adds the iodine. The water is kept there until it's needed through the Galley interfaces, which is represented on the left side of the figure. The other route goes through a series of check valves into tanks B, C, and D. C and D, the tanks C and D mainly provide cooling water for the evaporators, and tank B was originally set up mainly for the excess water to dump overboard. Okay. As Dick mentioned, iodine was used because it was used successfully in the Apollo lunar excursion module. It had a longer residual and less corrosive than chlorine. I believe during the Apollo era, the pipes were aluminum at that time, so they were much more conducive to corrosion. The iodine was also less hazardous than the manual chlorine addition that was used in the closed crew capsule and the command module. And again, that had to be done manually, so we're looking for a way to add a disinfection that didn't require any crew intervention. The chemistry for the iodine is essentially, it's the I2 combined with water to produce hypoiodous acid, which is HOI, plus hydrogen and iodide. It's an oxidizing agent. It inactivates the microorganism by attacking the cell membrane. The iodine is reduced to iodide, and this form is no longer biocidal. Okay, next slide. The iodine is added with a microbial check valve, which we call the MCV. It was developed by Umpqua Research Corporation. It is essentially an anion exchange resin, which is loaded with triiodide. Once the triiodide is on the triiodide is on the resin, as water passes through, the iodine as I2 is released into the water. Okay, as we've gone along, as we work with this system, we have learned that this temperature is temperature dependent. It's sensitive to anions in the water. For example, if we had a leak of the fuel cell and potassium hydroxide got through, this would potentially knock off iodine off the resin. So we always had to watch for leaks in the fuel cell. And however, it was also reasonably flow independent.
Jen, I might address that check valve just a bit. That technology was picked up out of Kansas State University. Dr. Lambert and Dr. Fina were instrumental in developing that resin initially. And then we picked up the technology and had a little contract at the Institute for Research in Houston that showed the adaptation that we use this for spaceflight. We then went out on a competitive bid, and that's when Umpqua received that contract. So that's kind of the background of that MCV, and it's really a neat operation. And Drs. Lambert and Fina, though, really need to get the credit for developing that resin. Unfortunately, I think they're both passed away now.
The next slide shows just how that microbial check valve looks like. It's essentially essentially a stainless steel cartridge about I'd say about 2 to 3 inches wide, and about 6 to 7 inches long, and it's packed with the iodinated resin.
There's a little side story to this one too, John. I don't know if you know that, but you see that is that item number 3 is your sleeve. Mm-hmm. That aluminum collar or sleeve was put on there. We originally had an interface control document with the Downey, North American Downey, North American, whatever it was, North American, and they had an interface drawing that showed, I think, 2.5 inches, but they changed it and didn't tell us, and they made it bigger. So we had a cartridge that's too small for the attachment, the device that was supposed to go in. So we came up with, we'll put an aluminum sleeve on the outside. So we had a gasket then that would fit the equipment that North American had made.
Next slide. The next major part on the water side is the Shuttle Galley. It is used to dispense the water, and it's dispensed through essentially a beverage adapter that has a needle on it. And the next slide shows how that needle adapter sort of works, and you can see how a pouch is one of the water containers is in there. I believe that one is actually a sampling bag. Okay. The next slide shows how the galley flow diagram is set up. Essentially, the galley has 2 inlets, an ambient inlet and a chilled inlet. The shuttle has a chiller that allows for water to be cooled before it goes in. The chilled side goes around directly into and can be dispensed through to what we call the rehydration station. The ambient side goes up and over into a hot water tank with a with a heater outside of it. The hot water tank is actually sort of located on the back end of the galley, okay, and it can circulate around. And you can see there's connections in between the ambient and chilled water side, so the crew member can adjust the temperature of the water to what they think they need. All right.
And also, John, does not it have a pump that you have instantaneous hot or cold water at the respective ports?
Yes, there's a cold water pump and a hot water pump.
And that's quite different than what we had on earlier flights. Matter of fact, Gemini, we had only ambient temperature water. Apollo, we had chilled water and ambient temperature. And then Skylab, we had hot and cold water. And then, of course, we recognized the need for hot water to particularly reconstituting food. So that's why we went through this elaborate procedure of pumping the water so that you'd have instantaneous hot or cold. Because you can't waste water. You can't just say, well, turn on the tap until it gets cold, because you don't have any place for the water to go. And same with the hot water. So that's why that plumbing arrangement looks kind of screwy, but that's how we came up with giving them temperatured water that was acceptable.
The galley also had besides the rehydration station, it has a personal hygiene outlet. A hose could be hooked up, and there was a microbial check valve located on that line also.
And that's to prevent back contamination to into the water system.
Some of the lessons learned along the way about the shuttle galley is obviously the need to maintain the disinfectant levels within the galley tubing to control microbial growth. We need the capability to remove disinfectant prior to dispensing, which I'll talk about a little bit later. And also a capability to add microbial filter in line prior to dispense was also desirable. These two last items came along as the program progressed, and we found that we had the need to remove the iodine.
The need to maintain microbial control became a different type of a problem in Shuttle, because we kept reusing the machine, and it would sit at the Cape for it could be months. So we, during that time, had to always maintain microbial control within the system as well. So that was a little different aspect than what we had seen before. As far as the water quality requirements, we really didn't have any until the Gemini program, and then by the Apollo program, recognizing that we were doing a lot of medical research in flight, we always maintained that we would have water quality as good as we had on the ground under normal conditions, because we didn't want that to be a variable in understanding the health of the crewmen. So that's why we pretty much adopted currently what the EPA standards are. I think they were called U.S. Public Health Standards. I'm not sure what the name of them were, but the standards basically emulated the potable water standards, with the exception of microbiology. Microbiology we allowed in, it's always been about 1 coliform forming unit CFU per 100 milliliters, or less than. So we pretty much adapted that as a requirement being 0, because we had no way to, just before flight, ascertain if an organism was a coliform forming unit or not. So we said, okay, we'll just eliminate everything and be on the safe side. And that's how we came up with that standard. And then over the years, we've made that standard less and less stringent. And I think now it's something like 50, and John will get to that detail, but I think it's like 50 organisms per 100 milliliters, but still we have no coliform forming units, CFUs. I think that's requirement still is 0. So that's how we got to that point, Dane.
Yeah, the original standard was 0 colony forming units per 100 milliliters, and that applied all the way through STS 78. After STS 78, we moved it up to 100 CFUs per 100 milliliters. And at that point, we added we also added the requirement for coliform bacteria analysis. And as the biologists got better at determining what was in the water and could generate the analysis faster, after STS-114, it was moved up to 50 colony forming units per milliliter.
Yeah, I misspoke a while ago. I said CFU is coliform. Those are colony forming units, CFUs, and that's what John was talking about. So just to be plain, we talk about colony forming units, which really is a catch-all phrase for almost any type of bacteria that might be growing in the water that would grow on the particular media that we're using. There is another requirement, and that's more or less called a total count. The other requirement is a coliform count, and those are enteric bacteria that represent fecal contamination of some sort, or ground contamination. And that count has always been maintained at 0 per 100 milliliters, and that's the one that's been consistent throughout early flight. But the CFUs, we recognize later on that if we could eliminate the coliform units, being i.e. then there's no fecal contamination, the other low number of units, colony forming units of 100 and then less than to 50, would be acceptable, and that's more or less acceptable also by EPA in their standards.
We also added after STS-121 a requirement for protozoa, and to meet that, it's actually a treatment technique. So that requires the source water to be filtered through a 1-micron filter. So the ground surfacing equipment was changed to add a 1-micron filter for the water that was used to service the equipment. And this was done through concerns with protozoa coming up, particularly Giardia and Cryptosporidium. The other requirement that has changed through the time was nickel. Nickel originally started out at 0.1 milligrams per liter max, with the chilled water was for reference only, and that was for missions prior to STS-121. After 121, the level was raised to 1.7 milligrams per liter, and I'll discuss that a little bit later in my talk. Okay, the rest of the requirements are essentially the U.S. public health standards that were done back almost in the, I guess, late 80s when they were developed, and we've maintained those throughout the program. Next slide. The water system methods for potable water analysis is the next one. Most of the analysis is done on the ground. Essentially, we do pH and conductivity. Most of the methods are essentially EPA-approved methods, or what's called standard methods. The pH and conductivity is done by electrodes, dissolved solids by a gravimetric method. For measuring carbon, instead of using biological oxygen demand, we have adopted the total organic carbon, and that was used by either the ultraviolet or heated persulfate oxidation. Turbidity was done just with a regular turbidimeter, nephelometric method. Color by a spectrophometric method. Metals, we started out in the program doing these by, I guess what you would call atomic absorption spectrophotometry, and as the technology changed, we're currently using inductively coupled plasma mass spectroscopy. Iodine is measured using a colorimetric method called leucocrystal violet, and we're also measuring the ethanol by a direct injection gas chromatography mass spectrometry method. Some other methods that are done by KSC are taste and odor, and an interesting one is we check for dissolved and free gas in the water using a syringe method that was specifically developed for the space program. The KSC people are still using the tryptone glucose extract method for total bacteria and doing the total chloroforms with what's called an M-endo broth. Okay. The system is serviced on the ground, and the ground surfacing system for the water is located in the orbiter processing facility at the Kennedy Space Center. The water system is serviced before each flight. Iodine is used as a disinfectant during the system servicing. And the iodine leveled in the GSE water tank depends on what the servicing objective is. For decontaminating the system, we use 20 to 30 milligrams per liter of iodine. Just for servicing tank A, which is the potable water tank, we use 2.5 to 10 milligrams per liter of iodine. Tank B, it's 2.5 to 6 milligrams per liter of iodine. And for servicing tanks C and D, it's 1 to 6 milligrams per liter of iodine. The iodine was originally added to the GSE water tank using a cartridge of iodine and the recirculation loop that you see. It was put in the entrance to the tank and the recirculation loop. This was difficult to control the iodine level, so they switched to adding the iodine with a 3% tincture of iodine solution. That means the iodine is added in a solution of alcohol. The alcohol is needed to make sure we get enough iodine in solution to add to the tank.
It's medicinal, by the way.
Yeah. The tincture, however, adds the alcohol. The problem is that has an impact on the water processor assembly if the water needs to be processed. One of the major components of the ISS water major contaminants in the ISS condensate water is alcohols, and so any alcohol that would additional alcohol could limit the life of that water processing equipment.
And the reason for that, by the way, might add, is that a lot of the water that's produced on the shuttle on the way up to the International Space Station is offloaded on the space station to supplement the water supply on the space station. And that's how this alcohol could eventually contaminate the ISS air reclamation or reprocessing?
The water reclamation system.
Water reclamation, okay.
So this for pre-flight sampling, excuse me, we take, before we fill the tank up each time, the ground surfacing tank, a pre-biocide samples are collected. So the tank is filled and a pre-biocide sample is collected when it's filled with deionized water, okay? And then we make sure that the water meets requirements before the iodine is added. Once the iodine is taken, then a post-biocide sample is taken to make sure the iodine levels are okay. The system is serviced, and then a post-service samples are collected from tanks A and B. Those are the ones that are used for drinking. And once those are okay, then the system's ready to go out to the launch pad. When it gets to the pad, we take samples at L-15 and L-3, and they're collected actually from the Galley port rather than from tanks A and tank A. It's actually tank A water, but the sample is taken from the Galley chilled port. Okay. There's post-flight sampling. Post-flight samples are also collected from tanks A or B. Tank A is collected from the Galley, and tank B is taken from the cross ties. Okay. For in-flight sampling, okay, no routine in-flight sampling is done on the shuttle. However, we have had some opportunity to take some samples as the program has progressed. We took some in-flight samples, were collected and analyzed for iodine during an high iodine investigation after STS-126. We also took some in-flight samples, were collected during a DTO of some Galley iodine removal assembly when we added the iodine removal equipment to the system. And once we got working with MIR and ISS, and we were transferring water from the ISS to the shuttle. A sample purge kit was flown as part of the water transfer hardware. That was mainly for sampling the water that was transferred to ISS. but that could also be used to take samples of the shuttle from the shuttle galley if needed, with a shuttle galley sampling adapter that we've developed for that kit. Okay. So next I want to go to with some of the challenges that we've had as the program has progressed. There's essentially 5 of them I want to discuss. The first one is the high iodine levels after STS-125. Then I want to talk about the high nickel levels that we've had and why the nickel levels changed. Talk about iodine removal, and then a little bit about a low iodine residual system we developed and tested. And finally talk about water transfers to ISS. The first challenge was after the Challenger accident, and we began to fly again. We noted that there were high iodine levels were observed by the crew during STS-26. In fact, Mary Cleve called down and said the water looked like iced tea. The post-flight samples we collected did not confirm these high iodine levels, so an in-flight iodine analysis kit was flown on STS-128, STS-28 and 30 to confirm the levels. The high iodine levels were traced to the influent temperature of the MCV inlet, increasing to 110 to 130 degrees Fahrenheit due to installation of insulation on the effluent lines from the fuel cells. This installation was installed during the downtime after the Challenger accident.
And no one told us.
No one told us that.
What happened here is that the microbial check valve is very much temperature dependent, and you can design the resin to work in any given temperature range to give you basically any iodine level you desire. So we had set the design of this for, I've forgotten what the maximum water temperature, inlet temperature, 70, 80
degrees Fahrenheit.
And
yes.
That gave us a residual of something in the order of 2 to 2.5 parts per million of iodine, milligrams per liter. And this, by going to 130, we were getting, John, I've forgotten, but much higher levels than that.
We were getting in the 10 to 15 milligram per liter range.
And so once we recognized that, we were able to then adjust the resin so that we get back in the reasonable range, the 2.5 parts per million.
Now, how did you track down the issue being that high temperature of the microbial check valve?
I was talking with Hank Rotter one day, and we were getting stuck back and forth and wondering why we were having this high level of iodine, and Hank indicated, well, they insulated that line from the fuel cell before because they were concerned it might freeze. And it was a valid concern, because when the water comes out of the fuel cells, it's very warm, it's hot, and there is a heat exchanger there, but it's only to get it down to an acceptable level from a system standpoint. But then once they put the insulation on the line, we were getting that hot water all the way down to the location for the microbial check valve.
If I remember correctly, there was also at the same time, there was a co-op student over in engineering that was also trying to determine the effects, the temperature effects just on the MCV at that time. Mm-hmm. That was her project. And so we sort of put the two together, okay? And so we actually flew some temperature tapes on the MCV, I believe.
Yeah, the liquid crystals.
Yeah. Okay, to determine what temperature it was getting at, to make sure we knew what the proper design temperature was. Okay. Next slide. This shows you the iodine analysis kit that we developed for this. This was developed using the food and liquid pouches that were used at that time. Essentially, the pouch was loaded. It's a clear pouch, so we could use a colorimetric method. We used a starch indicator, and the starch indicator was just calibrated, and you can see when there's iodine in the water, it turns blue. And we had developed a set of color standards to go up with it. You'll notice on the left side there's white or clear or yellow standards. That's without the starch indicator. In case it was really high, we could just some water into the system and compare and see how high it went. Okay.
Might add that those color coupons were film strips that Terry Slazak had developed for us. He worked out of the photo lab here.
This system is no longer available. It cannot be used now, mainly because soon after this, the food people changed to a food pouch that's not clear, and essentially just a bag rather than a pouch. Okay.
Couldn't get them to save any of those containers for you.
That's right. Yeah. So the first thing we did to correct that was we developed something called a microbial filter assembly. This was designed as an interim solution to remove the excess iodine in the water caused by the high temperature water passing through the MCV. The microbial filter assembly really just consisted of two standard microbial check valves located at the end of the inlet to the galley. One on the ambient side and the other on the chilled side. So see the next slide, please. Okay, you can see it there. They were just put at the inlet to the galley chilled water and the galley hot water tank. Okay, so as the temperature of the water cools, once it goes through the MCV at 130, but then goes to tank A. While it's in tank A, the water can cool. And so if the water is cooler as it goes through the MCV and has excess iodine, these cartridges, since it's a reversible reaction, would essentially suck up the iodine, basically, remove the iodine down to a useful level.
You should have seen the day I presented that to the program office. They said, well, if the microbial check valve here is putting too much iodine in, and you put another one like it, just exactly like it down here, how does it take it back out? How does it do that? And that took some real convincing at the time.
So the MFA allowed the galley to dispense the water at 2 to 5 milligrams per liter as the influent water temperatures were lower, compared to the 5 to 13. That's what we were getting prior to its implementation. All right. The MFA, however, had to be installed by the crew after launch each mission, so it was not the long-term solution. It was the desirable solution was to modify the MCV resin to operate at the higher water temperature. So a high temperature MCV resin was developed to release the 2 to 5 milligrams per liter iodine at 130 degrees Fahrenheit. This was first flown on STS-31. Excuse me. And has been successful in maintaining the acceptable levels of iodine in the water throughout the mission. Except for one flight where it came back and they turned out they forgot to add the resin. Okay. All right. So this is the end of the high iodine. I want to talk next about the nickel corrosion levels, or high nickel levels that we've seen, and why the nickel levels had to be changed. The nickel levels in the Atlantis post-service galley hot side samples, beginning with about STS-79, essentially exceeded the 0.1 milligram per liter requirement and reached all the way up to about 0.6 milligrams per liter. The levels in the chilled samples were seen up to 0.4 milligrams per liter, which is also above the 0.1 milligram per liter level. Although we initially saw it in the hot side, we began to see it in the cold side. The high nickel levels were actually traced to nickel leaching from the water chiller, as the brazed material in the heat exchanger used for the chiller contains 92% nickel. And so with age, the chiller was starting to corrode. So why were we getting also high levels in the hot level side? That's because essentially the galley hot side and the galley cold side shared the same tubing inside the galley. Okay, and so you can see it on both sides.
And that was as a result of trying to maintain the proper water temperature at the outlet, the hot water and the cold water. So there was a continual flow of water, and that's why that one line was used for each, and that's how the cold water nickel got into the hot water side.
So the engineers tried a reconfiguration of the chiller during an orbiter maintenance down period after the STS-86. However, these modifications didn't really help the situation. What we did find out, however, was that we could waive the high nickel levels in the post-service samples, as we found that the nickel levels were decreasing significantly after fuel cell activation during the launch countdown. Essentially what was happening was tank A is typically drained to 5 to 10% of its capacity after the L-3-day sampling and before the fuel cells are activated. That's because you had to make room for once the fuel cells activated, you got to get water in there. Once the fuel cells are activated, it's flushing the water through the chiller at a fast enough rate where you don't get the nickel corrosion. Also at 3 hours before launch, then the tank A is drained again to 40 to 50% of the capacity to meet the loading criteria for the flight. Okay, and so we confirmed that did this by taking some water samples that were collected during STS 98, 104, 106, and 112. These were some of the samples taken for the ISS water transfers. We take a look at the nickel levels, and they're all very low. This is confirming that decrease. Simultaneously, we were looking at, we had the JSC toxicology review the nickel limit, and they recommended to the National Research Council Subcommittee on Spacecraft Water Exposure Guidelines a new limit of 1.7 milligrams per liter. The 0.1 milligram per liter EPA limit that was originally imposed was actually rescinded by EPA when it was challenged in court by the nickel producers. They didn't have enough data to back it up, and so looking at it, we came up with our own limit. Okay, and that 1.7 limit was approved by the committee, and that's what was implemented at that time. And subsequently, we've never seen nickel levels up that high. Okay, the next thing I want to talk about is iodine removal. The iodine levels imparted by the MCV, which is approximately 2 to 5 milligrams per liter, were originally not thought to be sufficient to impact thyroid function. And all the original data showed that that was not a problem. However, during a 30-day chamber test of the ISS Eclipse hardware, we took a look and started measuring the thyroid-stimulating hormone levels from the test subjects that were and they found that these levels were increased during the test. And I think in general, why it wasn't seen before was this TSH test was a new test and was not found. Subsequently, the medics had a panel of experts come in, and as a result of that, they imposed a flight rule limiting the iodine ingested by the crew during shuttle missions to no more than 1 milligram per day. To determine how much we could do in the food or in the water, we first had to measure how much was in the food. Analyzed all the iodine in the various diets and came up with an average of 0.3 milligrams from the food per day. And if you back calculate, that means at 2 to 5 milligrams per liter, that allows only 16 ounces of iodinated water, which is about a half a liter. The unfortunate reality is the amount the crew consumed was 2 liters per day. So that meant we had to remove the iodine. A Galley iodine removal assembly was developed to reduce the iodine levels in the water consumed by the crew. And then we call that the Gira. The Gira initially consisted of 2 cartridges with activated carbonate and ion exchange resin assembled individually. The activated carbon removes the iodine, and the ion exchange removes the iodide. Okay, in terms of the thyroid function, it doesn't matter whether it's iodine or iodide, so you have to remove both.
Then on the TSH, I think that you said that technique did not exist before, but I think it did, but we need to go back and look at that. Yeah. But I think there were TSHs taken all the way through all the programs, but even to include Skylab, but I could be wrong on that one. Yeah, and anyway, what you said is true, that we didn't recognize up to this time that there was any impact of the iodine in the consumption of water. as far as thyroid function is concerned. And that's still, to some extent, I guess off the record, disputed around, because iodine is used in a lot of applications without any real issue at levels lower than this. That's kind of off the record.
All right. So after we flew the two cartridge design for a couple missions, and then an improved design consisting of a single stainless steel cartridge containing both the activated carbon and ion exchange resin in a single cartridge was developed. It's called the Actex. The Actex cartridge is installed in the Galley chilled inlet line, followed by a 0.2 micron filter. Can we see the next slide? It shows essentially the Gira assembly is shown around the Galley. It's in blue. The Actex cartridge is over on the left, followed by it's sort of wrapped around the Galley and put along the side of it, and then followed by the microbial filter, and then the hose snakes around and into the inlet to the chilled water. And a second MCV then is with a high temperature resin is also installed on the ambient line to the Galley. This MCV removes the iodine from the water, similar to the microbial filter assembly that we developed originally for the first high iodine levels. And that leaves about 1.5 milligram of iodine in the ambient water, which goes into the hot water tank. Since we're taking the iodine out prior to each sleep period, the Actex is disconnected from the chilled supply line, and iodinated water is recirculated through the Galley during the night to ensure microbial control. The crew has to install this equipment once they get on orbit during each mission.
Now, John, this is also to polish out the iodine for the water transferred to space station.
Yeah.
Okay. And that's why one of the reasons the Actex was developed, if you notice down here on the bottom, I think, John, that
the tube going out to the bottom on the
right.
left is the hose that's used to fill the contingency water tank containers used to transfer the water to ISS, and I'll talk about that a little bit later.
Okay.
Okay.
But it might noted that the Russians use silver as their bactericide, and that injection point there is that we would add a silver solution to each of the CWCs as they were being filled. Okay.
So I'm going to discuss that a little bit shortly, but before we do that, I want to get into another device we tried to use to develop to measure, to reduce the iodine. It was called the low iodine residual system. This was flown as a detailed test objective only. It's called, we sometimes call it LURS. It was developed as the Gira needs to be removed from the chilled supply line during each sleep period to allow iodinated water to recirculate through the Galley to maintain the microbial control. There was also problems if we had a two-shift mission and how we were going to maintain the iodine if the crew members were working around the clock. The LURS contain an ion exchange resin at the inlet end of the cartridge with a low iodine residual MCV resin at the outlet. The ion exchange resin removed the iodine and iodide from the supply water, and the low iodine MCV then released a low iodine concentration, about 0.25 milligrams back to the water to prevent bacterial growth. Okay, and how that was installed in the system is shown on the next slide. So obviously it makes it a lot easier to just essentially we fed all the water through the chiller and in through the LURS, and put a check valve to prevent the ambient water coming through, and then fed it into the both sides of the chilled and the ambient water. Okay. This one, I believe, was flown on STS-95. And what happened is we found there was an off-nominal taste in the water, was reported after activating the LURS. I remember staying up all night trying to figure out what that was. And the adverse tastes we actually traced to trialkylamine that were released from degradation of the Lear's resin during gamma sterilization. That was one of my most successful nights I think I've ever had. I had the answer for management by the morning.
It didn't taste good.
It did not taste good, no. How that was done was we had the next one ready to go, and so the engineer just took that one out of bond, run some water through it, and tasted it, and it was bad. And then he gave us some samples and say, "Tell me what's going on." Okay. It turned out the Lear was not tested after the gamma sterilization due to worries that the sampling of it would contaminate the resin. This decision was accepted by safety as the Lear's was considered a non-critical experiment. So the lessons learned from this one was that the experiments related to the life support system should be classified as critical hardware, and that certification testing of the hardware needs to be conducted in the final flight configuration. In terms of further development of the Lear's, this was about the time there was that last change in the microbial requirement, the 50 CFUs per 100 milliliters. And there was also some concerns with just using that low-level iodine, promoting iodine resistance. So based on that, we felt that we were able to meet the 50 CFUs per 100. Actually, it's 50 CFUs per milliliter without the Lear's, and so the further development of it was put on hold. And so far, the results have shown it's okay. There was unfortunately, there was only one mission where there was going to be a two-shift crew, and that was Columbia. And I had imposed some requirements on different ways on how to do the cleaning of that with the Gira, but we never got the results of that because of what happened during entry. The last thing I want to talk about is the water transfer from the shuttle to the ISS. The shuttle fuel cells produce more water than needed for crew consumption. So instead of dumping the water, we use contingency water containers have been used to transfer the excess water first to the Mir station during the shuttle Mir program, and subsequently to the ISS. The Russian potable water system on the Mir and ISS uses silver as a disinfectant. And as that is, iodine has to be removed from the shuttle water, and silver biocide is added, because if you add silver and iodide, you get a silver iodide precipitate. So we want to avoid that and use the same disinfectant that the Russians do. We also inject minerals to meet a Russian requirement for mineralized potable water. The minerals are added using a calcium and magnesium formate solution. This is not quite ideal, as the formate adds TOC to water. We still have not come up with a method of adding the minerals without adding the TOC. Most of the plain inorganic salts of calcium and magnesium are not soluble enough to develop a good, easy solution, and there's concerns on whether we would get the proper concentrations if we don't have a completely soluble solution. The next diagram shows a little bit more on how the water transfer works. This is the same as the Gira thing, except we showed a hose coming off, and off to the side we showed the contingency water container that was used to transfer the water. The contingency water container was actually, I believe, originally developed to store urine. Okay, and so it was adapted to use. It was adapted to use for the potable water. The material of that bag is what's called combitherm. It's a 6-layer material with a polyethylene interior. We have found that the polyethylene material is not compatible with iodine, so we cannot use it to transfer iodinated water. However, the material is compatible with the silver biocide. We add the silver with a silver fluoride solution, And so it works quite well with the for transferring water with the silver biocide. The only other thing that we have found with the contingency water containers is the middle layer is a nylon, and we have found that there's some leaching with time of caprolactam, which is the monomer of nylon. All right. So one of the lessons learned on the water transfers is you have to be very careful about the bag material that you use for transferring water. And for the most recent work with ISS, and when we're transferring iodinated water, we have developed a new bag called a iodinated CWC, which is made out of Teflon.
Isn't that the one that Paul was working on?
We also have another one. This one's a smaller one at 10 liters. There was one called. We also have another one called a payload water reservoir. Actually, the payload water reservoir is a 10-liter one. The ICWC is a 20-liter one, so it's compatible with the Russian water container size of 20 liters.
And that's the stuff that Paul Mudgett was working on.
Yeah.
Yeah. They had the real fancy welding process to weld the Teflon.
The Teflon is put together with a laser welding method by American Fluoroseal. The last picture shows the kits that are used that were developed to add the minerals in the silver biocide. The upper left is the silver biocide kit. Those are actually syringes. You don't see them in there. They're wrapped. They're wrapped essentially in a amber plastic bag to prevent the silver from photo degrading. The mineral syringes are about 100 milliliters, so that's, you can see, and that's how big they have to be to fill up a CWC with a soluble solution of the calcium and magnesium formate. Okay, so if we were trying to use inorganic salts, it would be the syringe would be way too big. Okay, the final, the bottom picture shows the sample purge kit. What do we mean by a sample? It has the equipment to take the samples once the water is transferred into the CWCs. We take a sample of it to make sure it's okay. And then the purge part is some sample bags that are used to purge the water transfer equipment before we start filling up the bags. So that's all I sort of had prepared for today. Did you have anything else you wanted to add?
No.
A lot happened in terms of potable water dispensing on ISS. What was developed was called a potable water dispenser. It was not a full galley per se. They decided to try to maintain the temperatures. They added the Actex cartridge right into the dispenser. But from a water quality standpoint, it would be good to put it right at the outlet, at the dispense point of the dispenser, along with the microbial filter. The problem with that was maintaining the temperatures of the water. So it ended up, I guess, the decision was made that the temperature of the water was more important than maintaining microbial control throughout the galley, and so those were put at sort of the inlet point of the dispenser, and that seems to be working as long as we use the potable dispenser quite often. But if the potable water is left stagnant because it's not being used, i.e. the water processor is down or something, then we're having problems with microbial growth in that system. So the same issue of maintaining the residuals within the galley and the potable water dispenser are still with us.
So you're talking about the shuttle, right?
That's on ISS now.
Oh, it is on, okay.
That's the dispenser on ISS.
Oh,
yeah.
okay.
Okay. I know there was a second smaller dispenser that was developed for Shuttle for some of the other missions that we didn't discuss today. I didn't think we were going to have time.
We've obviously been very limited with monitoring that we can do with
Well, we have much more monitoring on ISS, and we were able to justify that because of because the water is being recycled from condensate in Europe. So on ISS, there is what's called a total organic carbon analyzer, a TOCA, to measure the TOC of the water as it comes out. We're taking weekly samples with that. When we were going back to Constellation, it was difficult to try to get the requirements in to still do the sampling, in-flight sampling against the same with Shuttle. Particularly since the Constellation capsules were so weight limited.
Dick, what was the beginning of the TOCA? That was, maybe it's true to say it was somewhat controversial because we were just measuring total organics and couldn't necessarily tell.
Excuse me. I'll have to call you back.
I'm wondering if you could say just a couple of words about what your thoughts were in terms of your philosophy about monitoring in the total organic carbon analyzer.
Yeah, those requirements, we had a requirement at one time that we're going to have the GCMS
total organic carbon and a GCMS spec
and also a spectrophotometer. And those requirements kept getting cut back and back because of funding and because of so we managed to keep the one thing that probably gave us the most information, and that's the TOCA, because it gave you an appreciation of your total organic load. We've always thought that we could probably do a pretty good job with the minerals, the ions, with ion exchange resin, and that stuff is really well known. So as long as they're running through those beds and get a decent conductivity reading, we thought we could buy off on that and stick with the TOCA, and that's how we finally got just down to the TOCA. It was funding and all the other requirements.
It's interesting, John, you might say a few words about what's going on right now with the TOCA and what you recently found and how the instrument, I think, really has proven its worth in recent weeks.
During the summer, starting in about June, we've had the TOCA has shown an increase in TOC produced by the U.S. water processor.
On board station.
Yeah, on station. But before that time, essentially all the data was essentially what we call below the detection limit. It was a little in the noise in the bottom, and starting about mid-June, it started to go up, and so and it's been pretty linear. What I find, we took it to the program, to the engineers, and we were worried everybody would come back and say, well, the TOCA is not giving good results or not. But everything showed the TOCA was good, and the only thing we did not have done lately was we had lost a calibration run, but they let us get a calibration run real quick that showed it was still working right. And so everybody was believing the data quite well. And so just 2 weeks ago, they changed out the multi-filtration beds up in the water processor, and we got a first result back, but from after that, but the water in the tank was still from the previous processing, and we're still waiting to get another sample back to see how whether the changing the beds out has improved things.
Well, isn't the conjecture that you have a higher input of organics to that filter?
That's what they're guessing. There's two possibilities. One is there's a higher organic level. We have limited condensate samples that were coming down. That was one of the issues that I had along with ISS along the way. I originally had a requirement to measure, take samples of the condensate, and some of the program managers indicated that, well, this was not really a medical requirement, an ECLS requirement, but it should have been an ECLS requirement, and they should put it in if they wanted it. And so, however, so it got to that level, ECLS didn't want to come up and say we want to come up with the money, didn't want to justify the money there. However, as soon as they got it back up, they figured out a way to still get those samples. All right, so, but I don't get them often as I'd like. And due to some issues with the water processor before then, the sample I got was from the lab condensate tank, which had been sat stagnant a while. That was my most recent, and it was high, but we're not too sure about it. And so we're not too sure whether it's due to high condensate, or the other issue was we had just changed out the catalytic oxidizer on it. So the worst case could be the catalytic oxidizer is not doing what it's supposed to, and that would cause some difficulties because there's not a spare on board right now.
So when we go beyond low Earth orbit and maybe start going exploring space, go out to Mars, let's say, what kind of monitoring do you guys believe should be done in the water system?
It really depends on what you're using as your source of water. If you're just using a stored water and not recovering the water and recycling it, then we can get by with probably just a little, what we call a little water monitoring kit. We've been developing one based on colorimetric solid phase extraction called the CSPE, or the
Whatever.
CWQMK. Yeah. Okay, is our latest name for it. And that's being currently flown on ISS as a DTO to measure iodine and silver, actually. So you would mainly use it to make sure your disinfectant levels stay the way it is, similar to what was being monitored during the Skylab era. If you end up recycling the water, say like a Mars or lunar base, where you probably would, then you would at least need a TOCA. And I know the first thing that happened when the TOCA numbers at ISS started going up, they'll say, "What is it?" And I say, "I can't tell you until I get a sample down." Okay, because we don't have the capability to measure specific organics. So it would be nice to have if we can develop it and get the funding for it, but the question is whether you can justify it.
I think on missions those length, I think you're going to have to have some pretty sophisticated instrumentation on board for chemical microbiology, inorganic and organics. Inorganics probably not as critical as the organics, which means a TOCA and maybe some sort of a GCMS type capability. I'd like to talk about that LERS event. That was some interesting things. That was the low iodine residual system. We got into a real time push on that one and just literally didn't have time to do the post-testing after the irradiation. And talking with all the people, all the experts at the time, there was general consensus that there should be no problem with irradiating the iodinated resin. And so as a result, we didn't do that test afterwards. Part of the time factor was that we had to have human experimentation research. What do you get the approval to do human testing?
The Human Use
Committee, yeah. And that's the only way we could have determined if there was a taste in the water, and we couldn't get that done in time to support it. So we made the decision not to just go ahead without testing it after the fact, and that's where we got in trouble. So it's, haste makes waste, and that's learned many times over. I think that one of the things that's helped us during the development of the shuttle and space station systems and the Skylab system is that we had that experience base from the Apollo program to say what we needed to do to make sure that we had a good system. That's pre-flight, the addition system, the water addition system, system materials, the bladder, going from an elastomeric bladder to a stainless steel bellows to eliminate the gases, and all those things we learned back in those flights really contributed to a good design on the workshop and the space. And we've had very few real problems. The workshop, the
Orbital Workshop had, or the Skylab, had virtually no problems at all. That system was very, very well behaved.